Hi, welcome back. In this lecture, I would like to introduce the topic of quantum arithmetics. That is, how to compute in superposition using the arithmetics operation we know from the classical world. So differently from many conventional arithmetic operation that we have in the classical computing, our basic QPU operation must be reversible. And this is a constraint we have from the fact that we are dealing with quantum systems. So whenever we need to implement a quantum circuit for doing quantum arithmetics, we will have a constraint on the QPU quantum circuit from the fact that we need to ensure that the operation is reversible. So a simple operation like 5 plus 2, that is equal to 7, is actually not reversible. So we can go from here. However, to go back from 7 to 5 plus 2 is not possible, at least with a very basic implementation. Not possible because it could be 7 plus 0, 6 plus 1, can be many other options, right? So given the 7, we cannot back to the addends. So the simplest way of implementing any conventional circuit in our QPU is to replace the circuit with the equivalent conventional circuit only using reversible operation. For instance, we saw the Toffoli gate. There will be a major tool for us to implement quantum primitives. So let's go a little bit deeper on the issues of implementing quantum circuit to perform arithmetic. One of the major constraints that we have is that qubits cannot be copied. And this is because of an important quantum computing theorem that is called the non-cloning theorem. For this reason, we don't have any copy instruction in quantum computing. However, a QPU can move qubits using the swap or exchange QPU instruction to swap the qubits with other qubits. But no QPU will ever implement a copy instruction because this is not possible according to the law of quantum computing. As a result of this, the assignment operation, the equal operator, cannot be used to assign one qubit a base value to another. Right? So what we saw before, A plus B is equal to C. See, this cannot be actually implemented in quantum computing. The only things that we can actually do is make arithmetics that consist of just updating. Incremental operation like we have A, that is our variable, and then plus plus, that means that this is also basically incremented by 1, the values in 1, and other update operation like minus minus, that is the decrement operator, or multiplying to the values of a certain register. So important point is that we cannot copy, so the assignment operator cannot be used in quantum computing, and all the arithmetics that we actually implementing are updates. So increment, decrement, multiply per same value, the values of a quantum register. I told you that the assignment operation cannot be implemented. So suppose we have two QPU register A and B, and we ask for a simple operation C equal to A plus B. So this is actually the analogous how CPU performs an addition in conventional digital registers. However, this approach violates both the reversibility, so we cannot go back from C to A plus B, and also the non-copying restriction, because we cannot actually assign, so cannot do the assignment operation. So this is some important part that you need to take out from this lecture. If we compare traditional with quantum computing arithmetics, we have that conventional digital logic has plenty of highly optimized approaches for performing arithmetic operation. Conventional operation are expected to operate on a single set of inputs at a time, but also there are some, we can use parallel computing to do it, but in the basic implementation, conventional operations are sequential, unless we go to parallel computing. However, in quantum computing, we can use the fact that we can compute in superposition. So that means that when we do, for instance, an increment operation, we want quantum arithmetic operation to affect all the values in the superposition. But let's see an example on how to do this parallel computing in superposition using quantum update. So this is an operation that we're going to look at in the next lecture, that is the increment operation. Do not worry yet about the quantum circuit to implement this increment operation. I just want to here to get basically the nature of the increment operation and get an understanding or a first intuition why we say that calculation in superposition are also somehow calculation in parallel. Well, the reason is that we can have this quantum register in a superposition of 1 and 5. So these are two different states. What we want by doing our quantum arithmetics that can operate on a superposition, we're going to apply an increment operation to this state here, plus, and also here. So we're going to do our quantum gate will provide, it will sum up 1 to A, so update, so the state 1 will become 2, and the state 5 will become. So this is the last slides of this lecture, and in the next lecture we're going to look at more in detail how to implement this increment, but also decrement and other operation using a quantum circuit. Talk to you soon.